Welcome to our quantum deep dive. Today, we're exploring a truly extraordinary state of matter that gets colder than deep space and behaves like one single giant super atom. It's called the Bose-Einstein Condensate, and our guide for this journey is a fantastic essay by Jörg Oe Schneppot. Now, this might sound like something straight out of science fiction, but I promise you it's very real, and it's already starting to change our world. We're talking about a phenomenon where the bizarre, fuzzy rules of the quantum world, the stuff that's usually hidden away at the subatomic level, suddenly become visible to the naked eye. Okay, so let's get into it. Here's our roadmap for today. We're going to start with what this stuff actually is, then look at how it was predicted, the absolutely incredible journey to create it, its super strange properties, and finally, where this amazing technology is taking us. Right, let's start with the basics. We all learn about solids, liquids, and gases in school. Maybe you even know about plasma, the fourth state of matter. But what happens if you take matter and make it colder than anything, and I mean anything, in the known universe? Well, you get the fifth state, the Bose-Einstein Condensate. A BEC is this amazing collective state where individuality completely vanishes. I want you to picture a huge crowd of people where every single person suddenly starts moving, breathing, and even thinking as one single unified being. That's what happens to atoms in a BEC. They literally stop being individuals and merge into one macroscopic quantum wave. It's wild. Exactly. And to get how this is even possible, you have to know that in the quantum world, all particles basically fall into one of two categories. You could say it all comes down to whether particles are, social or antisocial. Think of it like a big party. Okay, so you have bosons. They're the socialites of the particle world. They absolutely love to crowd into the exact same space, the same energy level. If one boson finds a really great low energy spot, all its friends are more than happy to pile right in on top. But then you have fermions. They are the ultimate loners. Because of something called the Pauli exclusion principle, they insist on having their own unique quantum state, their own personal space. So a BEC is basically what happens when you throw a huge party for bosons in a very, very cold room, and they all decide to cram into the exact same spot. So here's a crucial point. This totally wild idea wasn't first discovered in some fancy lab. Nope. It was actually predicted on paper, long before we had the technology to even dream of creating it. For the better part of a century, it was just a ghost in the mathematical machine of physics. And this timeline just shows you what an incredible story it is. Look at that 70-year gap. It starts back in 1924, when Satyendra Bose sends a paper to Einstein. Einstein realizes this math could also apply to atoms, and he predicts that if you could get them cold enough, they'd all just collapse into a single quantum state. But the temperatures they were talking about were so insanely low, it just stayed pure theory for decades. Then, finally, in 1995, it happened. Two different teams pulled it off, and for that incredible work, they shared the Nobel Prize in 2001. So, the big question is, how did they finally do it? How do you get something colder than the vacuum of deep space, which sits at about 2.7 degrees above absolute zero? Well, the answer involves some seriously clever physics. Yeah, you can't just stick them in a tiny refrigerator. You have to remember, temperature is really just a measure of how much atoms are moving and jiggling around. So to make something colder, you have to slow its atoms way down. And the process they came up with is brilliant, and it happens in two main stages. First up is laser cooling. You use lasers as like photonic breaks. You tune the laser light just right so that any atom moving towards the laser beam absorbs a photon and gets a little push, slowing it down. It's like running into a headwind made of light. This gets you incredibly cold, but it's still not enough. Step 2 is something called evaporative cooling. And this is a bit like cooling your cup of coffee. You blow across the top, right? You're letting the hottest, most energetic steam particles escape, and what's left behind gets cooler. They did the exact same thing, but with atoms in a magnetic trap. They just gently lower the walls of the trap and let the speediest atoms fly away. And this whole magic trick happens inside a device called a magneto-optical trap. You can just think of it as a special cage made of light and magnetism. It uses a bunch of lasers and carefully shaped magnetic fields to hold the atoms perfectly in place while all that cooling is going on. The final temperature they reach is just astonishing. We are talking less than 200 nanokelvin. That is just billionths of a degree above absolute zero, the theoretical point where all atomic motion is supposed to stop. It is colder than anywhere else in the known natural universe. Okay, so creating a BEC is this incredible achievement, but the real magic is what it lets us see. Because with a Bose-Einstein condensate, we can actually witness quantum phenomena, things that are normally totally invisible on a scale that's large enough for us to observe directly. This is where it gets really weird and wonderful. This right here is the payoff. You get a substance that can flow forever with zero friction. It's a true superfluid. If you could stir it, it would literally never stop swirling. But it doesn't just swirl. It forms these perfect, tiny whirlpools that are quantized. And since all the atoms share one single wave function, they're perfectly in sync, or coherent. So if you take two of these BECs and drop them on top of each other, they create interference patterns, ripples of high and low density, just like two waves in a pond. It's spectacular proof that matter, at its very core, behaves like a wave. Exactly. And as Sneppet points out in his essay, this isn't just about creating some weird blob of ultra-cold matter. It's about creating a laboratory. It gives us a platform to poke and prod at the fundamental rules of the universe. It's basically a magnifying glass for the quantum world. Okay, now don't worry, don't let the math here scare you. The really crucial point is that this single equation, the Gross-Pitayevsky equation, is basically the mathematical recipe. It describes the shape, the motion, and all the behavior of the entire superatom all at once. It's what allows physicists to predict and understand all those bizarre properties we were just talking about. So why does all of this really matter? I mean, beyond being incredibly cool science. Well, this fundamental research is now becoming the foundation for a whole new generation of technology. A BEC isn't just something to study anymore. It's becoming a tool. First up, atom lasers. So instead of a beam of light, I want you to imagine a perfectly coherent beam of matter. By carefully letting atoms leak out of a BEC, we can create just that. And these ultra-precise beams of matter could be used for things like atomic-scale manufacturing or building microscopes with unbelievable resolution. And because of that wave-like nature we talked about, BECs are perfect for something called interferometry. Atom interferometers are insanely sensitive to the tiniest changes in their environment. This means we can build things like gyroscopes for navigation that are so precise they would never need a GPS signal, or sensors that can map out minerals deep underground just by measuring tiny wobbles in gravity from the surface. You know, there are some problems in physics, like trying to understand high-temperature superconductivity, that are just way too complex for even the world's fastest supercomputers. But we can use a BEC to build a physical model of the problem. You can arrange the atoms in what's called an optical lattice, think of it like an egg carton made of light, and you can simulate how electrons behave in a material and just let nature do the heavy lifting and compute the answer for you. The best atomic clocks we have today are already just mind-bogglingly accurate. But the extreme stability and cold temperatures of the atoms in a BEC give us a way to build the next generation of clocks. And we're talking about clocks that could be thousands of times more accurate than what we have today. So precise, they could detect the warping of space-time caused by gravity over just a few centimeters. And believe it or not, we're even taking this technology to space. The Cold Atom Lab on the International Space Station is doing exactly this. See, in the microgravity of orbit, the atoms can be observed for much longer. We're talking seconds instead of milliseconds. This allows for measurements with a precision that's just impossible down here on Earth, pushing the limits of what these quantum systems can teach us. So when you step back and look at it, we've gone from a prediction scribbled on paper in the 1920s all the way to a quantum toolkit operating in space. The Bose-Einstein Condensate just shows us the incredible power of quantum physics. And it really makes you wonder, right? If we can engineer matter at this fundamental level, what problems are we going to solve next? We've really only been able to scratch the surface today. So for a much deeper look at the theory, the experiments, and the future of this incredible state of matter, you should definitely check out the original essay by Jörg O.A. Schnepp. You can find it at schneppot.de. Thank you so much for joining our quantum deep dive. Goodbye. Goodbye.
Schneppot.de is a private project by Jörg O.A. Schneppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.